This is a video proven by mathematical induction that the derivative d of x to the n dx is equal to nx to the n minus 1. This is a proof by principle of mathematical induction. So let's start off with the base case. Proof for n is equal to 0. So let's do that then. So we've got dx to the n over dx is equal to n x n minus 1. So if we insert a 0 there, so the derivative of, just gives it a constant, is just 0. So that is 0 multiplied by x to the 0 multiplied by x to the negative 1. And anything multiplied by 0 is 0. So we proved the base case. The next thing we need to prove, or assume rather, assume true for n is equal to k. So we've got gx to the k, x is equal to k, x, k minus 1. The third thing, prove true for n is equal to k plus 1. Let's do that then. Dx to the k dx is equal to k plus 1 x to the k. Let's get some more space. Get rid of this. Okay, so we need to prove that the left hand side is equal to the right hand side. So let's work on this left hand side. Should be k plus 1. So we've got d to the x, k plus 1. This is the same as x to the k x to the 1 d dx, all of this. So this is a product. So we leave the first and we differentiate the second, which is dx with dx. Then we leave the first, which is just x to the k. Leave the second rather, and differentiate the first. We know that dx of dx is just 1, so we get x to the k multiplied by 1, and we use our statement here. We've got dx to the k is equal to k x minus 1. So let's do that then. So we've got k, x, k minus 1 multiplied by x. And that's the assumption we've made. So let's tidy this up then. We've got x to the k. That's a bit of a mess. We've got x to the k plus kx to the k. And we can take out the k there to get 1 plus k, 1 plus k, x to the k is what we are required to prove. So proved by principle of mathematical induction.